Hi, a while ago I reviewed UNI-T's UT8805E 5.5-digit bench multimeter, and I'm very impressed with its measurement accuracy and build quality. For those who haven't watched my review and teardown videos of the UT8805E, I will put the cards up here and will leave the link in the video description as well, so you can check them out at your own leisure. Now, what's better than a 5.5-digit bench multimeter? Of course, a 6.5-digit one. And that's exactly what I have here. Let me bring it over here, and you can see. This is UNI-T's UT8806E, a 6.5-digit or 2 million counts bench multimeter. In this video, we'll take a deeper look of the UT8806E and we'll do a teardown of this meter in the next video. Be sure to subscribe to this channel as I have more videos coming up featuring the UT8806E. Thanks UNI-T for loaning me with this UT8806E so I can make these videos for you. After all, a 6.5-digit bench multimeter is not something most hobbyists got to see every day. You might have noticed that this one says UT8806 on the front panel here instead of 8806E. I was told that this unit was from an early production run and it should be identical to the 8806E. On UNI-T's website you will only find the E version, but in the product manual, the pictures still show as 8806, as you can see here. Anyway, with the model number out of the way, let's take a look at the physical appearance of the 8806E and compare it to that of the 8805E while I still have that meter out here. At a glance, the front panels of these two meters are largely identical, but if you look closely you will see that the 8806E is about 1 centimeter narrower than the 8805E down here. This is a little bit unusual, I guess, as I would have expected UNI-T sticking to the same dimensions. Now, I realize the video camera probably distorted the image a little bit, so let me actually use a ruler to measure it, because now you can see this one looks shorter than the UNI-T UT8806, but they are actually at the same height. Okay, so let's first take a look at height. You can see they're roughly about 10 centimeters, and both are the same height. But width-wise, you can see from the bumper to the bumper, here we have about 22 centimeters, and here we have about 23, a little bit over 23 centimeters. So that's the size difference I was talking about. You can see the subtle size differences on the left side here. On the 8805E, you can see the USB symbol is to the left of the USB port because there's a little bit more space. But on the 8806, you can see that the USB symbol is underneath the USB port because the spacing is narrower. If you look closely, you will see that the buttons on the 8806E is spaced closer horizontally compared to those on the 8805E as well. Now let me turn them to the side so you can see the side profile here. And you can see that the 8806E is also quite a bit longer, or deeper, however you want to call it, compared to the 8805E. So although these instruments are stackable, these two bench meters don't quite stack together that well, as you can see here, due to their size differences. And let me turn it again so we can see the rear panel here. As you can see here, the 8806 also has these rear inputs. And these inputs are mainly used for automated testing. On the 8806E, you can select between the front panel input and the rear panel input via a push button on the front panel, which I forgot to show you earlier, but I will show you in just a bit. Besides the rear input jacks, everything else looks pretty much identical between these two meters. On the 8806E, we have a VCM output BNC, which outputs a 1 microsecond pulse on the completion of every sampling. The external triggering BNC port supports triggering from an external source. We also have an Ethernet port that supports the VXA11 protocol, a USB port for PC communications, and a RS-232 serial port as well. You can program the meter using Skippy commands, which I'm not going to cover in this video. By the way, the 8806E also offers GPIB port as an option. Obviously, this unit doesn't have that. If it has that, it would be right here. Alright, let me put the 8805E to the side and concentrate on 8806E. And by the way, here's a button I forgot to show you earlier. This is how you switch between the front panel inputs and the rear panel inputs. The probes supplied with the 8806E are identical to those supplied with the 8805E. These are very high quality probes, but I do wish the tips are gold plated as they are not. Alright, let me power it on and we'll do some measurements. Technically speaking, we should probably leave it powered on for at least an hour before performing any measurements for the maximum accuracy, but for the purpose of this video, it probably doesn't matter that much. And yes, just like the 8805E, we also have a fan on this 8806E. Oh, actually, before I forget, let me show you the calibration certificate. Yeah, as you can see, this particular meter was last calibrated last December. What I wanted to show you though is what kind of instruments they used to calibrate this 6.5 digit multimeter. Well, as you can see here, they used the Fluke 5520 and Fluke 5522 calibrators. These calibrators are very expensive, of course. If you have to ask, you probably can't afford it. Even a used one costs more than a luxury car. In case you wonder what instruments they used to calibrate the 5.5 digit 8805E, well, let me show you. And you can see they actually used the Keithley 2001. That is a 7.5 digit multimeter. Let's first take a look at the DC measurement mode, as that's the mode it boots into by default. The user interface of this 8806E is very similar to that of the 8805E, but there are a few key differences here. Instead of having just the fast, medium, slow measurement speed on the 8805E, the 8806E has this NPLC setting. NPLC stands for the number of power line cycles, and it controls the integration time. To achieve the 6.5 digit resolution, the integration time needs to be greater than 1 power line cycle. If you wanted the fastest update rate, you can choose the 0.006 power line cycle, and it will give you roughly 4.5 digit resolution. Everything else in between will give you 5.5 digit resolution. And let me do a quick demonstration here. Right now we're updating roughly twice per second, and let's change the number of power line cycle. We're going to change it to 1, and you can see the update rate is faster now. And of course, we update to, let's say, 0.006, sorry. That's the fastest. And now we only have a 4.5 digit resolution, but you can see the update rate is insanely fast. Of course, once in a while you see this pulse, that's because we're doing the automatic range switching here. So let's change it back to 10. And you can see that's the default. And of course, for maximum accuracy, you can change to 100 power line cycles. Of course, this will be very slow. You can see here, we're roughly measuring about once every 2 seconds. So let's change it back to 10. Also, you can see we have this auto zero option here. When enabled, the meter disconnects the input after each measurement and takes the zero input reading. The displayed measurement results is then the difference between the measurement and the zero input reading. This minimizes the error caused by any bias and thermoelectric effect of the input circuitry itself. Of course, the downside is that it does slow down the measurement quite a bit. So if I disable it, you will see that the measurement speed becomes much faster with the same integration time setting. But of course, the reading variations become much more pronounced when nothing is connected. So let me change it back. And you can see that with nothing connected to the probes, even though we have the auto zero set to be on, the readings are still jumping quite a bit. And that's because the meter is in auto mode and it has more than 10 gigohms input impedance when the measurement range is at or under 20 volts. This input impedance is very similar to that of the 8805E, and I did a video measuring the actual input impedance of that meter. If you are interested, you can check out that video, which I'll provide a link in the video description below. Now, since this is a 6.5 digit meter, we have a 0.1 microvolt resolution in the 200 millivolt range. We actually can test this using my MV216A voltage standard. So let's do that. And I have connected to the MV216A, and you can see with the MV216A output enabled, setting at 0 volt, we do have some offset. The offset here is about 4 microvolts. So let's do a couple of things. Let me actually first change it to 100 power line cycle. This way we can have more stability in the measurement readings. Also, I'm going to route it out, so we start with roughly 0 volt. And you can see that the measurement is actually very sensitive. Even after we zeroing it out, it still has some reading and is varying in this last digit. But anyway, let me start adjusting the output from the voltage standard and we'll see what we get on this meter. Alright, so now let me start incrementing from the voltage output. Let's do 0.1 microvolt at a time. 0.1 microvolt. And of course, because that actually is at the limit of the resolution, so it does take a few seconds to register the reading here. So let's do 0.2, 0.3, and you can see we are able to register that last significant digit. Of course, it is still jumping all around the place because that is at the limit of the resolution here. 0.4, 0.5, 6, 7. If I let it sit long enough, statistically speaking, that would actually converge to the digit I am dialing in here. 8, 9, so this is 1 microvolt. And if you remember, when we were at steady state, we were showing minus 0.4 microvolt before. So roughly speaking, right now it's actually at exactly 1 microvolt. So let's increment it 1 microvolt at a time. 1, 2, 3, 4, 'and remember, right now we're at extreme low voltages, so the performance actually is quite impressive. As you can see, we are able to discern all the voltages we're dialing in here. Of course, it takes a long time for the reading to settle. 6, 7, 8, 9. You get the idea here. So this is at 10 microvolts, and you can see the reading is pretty much exactly what we're dialing in here on the MB216. And right now, of course, the measurement speed is quite slow. Let me change it to 10 power line cycles, and we'll do a few more measurements, this time with higher voltages. Hopefully the readings will be more consistent here. So let me give that a go. And now let me change it to 0, and I'm going to change the range to, let's say, 10 volts range. I'm going to do 1 volt. You can see 2. Remember, this is a 2 million counts meter. So at 2 volts, you can see we have 1, 2, 3, 4, 5, 6 digits resolution. And if I change to 3 volts, of course, we'll lose 1 significant digit. So now we're at 5 digits here. 4, 5, 6, 7, 8, 9, 10. As you can see, the resolution of a 6.5 digit multimeter is quite impressive. Having high resolution is just one of the benefits, of course. Another benefit is the high dynamic range. And let me demonstrate that. So right now we're in auto mode, and you can see the range is set to 20 volts. So let me actually adjust it to, say, 1000 volt range. And you can see that even when we set to 1000 volts, which is the highest DC range, we still have a resolution of 1 millivolt, which is very impressive. Anyway, let me set it back to auto. And if you press on the history, you will see that we have some statistics of the measurement. And of course, you press list, you will see the list of the measurement we just had. And of course, you can go down to next page, so on and so forth. And we can go to the last page. You can see 10 volts we just measured here. Now let's move on to the AC measurement. For AC measurement, the meter is capable of measuring frequencies from 20 Hz all the way up to 1 MHz. Also, just like the 8805E, this meter also has a dual display setup, and in AC measurement mode, it can also measure the frequency. So let me show you that. So to do that, we press display, and you can see we have the dual measurement, and I can enable it to frequency. And let's measure the mains voltage using the setting here. So you can see the mains voltage measurement has quite a bit of resolution here. And by the way, you probably noticed that we have this filter option here. And according to the manual, this should be set at the highest frequency, that is below the frequency being measured. So for mains voltage measurement, we should set it to 20 Hz, which is the default. But if you see here, we also have 3 Hz and 200 Hz. With the correct filter setting, the measurement accuracy is further improved. So that's a demonstration of the dual display capability here. Obviously, in different ranges, the secondary display is going to be different. Also, I should point out we have a few different display options here. You can see we can display with the numbers, bar, graph, and let's take a look at that. And also we can display trend and display histogram. So let's take a look at the bar graph here. The update rate of the bar graph is exactly the same as the digit update rate here, so it doesn't update any faster. But we have a few parameters to play with here. You can change the scale and center so it can help you visually identify whether the reading is in the correct range. And that's actually useful in automated testing when you have to tend quite a few of these displays all at once. So you can change, for example, the center, and you can change the span here. You get the idea. So you can fine-tune these settings to set a very specific range. Of course, we can display trend, and that helps you visualize the measurement against time. And you can see, of course, right now the range is very tight, that's why it's jumping all over the place. But in actuality, we're actually very close to the 120 nominal value. And of course, we can display histogram as well. The histogram is very useful. For example, right now I'm measuring mains voltage, and if I let it sit for a while, what do you think we would see on the histogram? I had let it run for a few minutes now. You probably have already guessed it. The distribution looks pretty much Gaussian. The maximum frequency can be measured is spec'd at 1 MHz, so let's actually verify that. Right now I'm using a signal generator outputting a 1 volt RMS signal, and you can see right now it's at 100 kHz. So let me increase that frequency here. So let me do 500 kHz, and you can see we're still having the 1 volt reading. And let's go to 1 MHz. And you can see essentially we're getting the same voltage reading. And we can of course increase the frequency a little bit, 1.1. And you can see the maximum frequency you can measure is actually just 1.1. As right now I'm setting at 1.2, it's no longer able to measure the frequency, but nevertheless, the voltage reading is still pretty much 1 volt. Now let's take a look at the current measurement. I'm going to change it to the 200 milliamp range. By the way, it has two ranges. One is 200 milliamp and another is 10 amps. These are through different input jacks. Let's do the 200 milliamps, and let's change it to DC current. You can see the terminal here, we're setting at 200 milliamps. Of course, you can change it to 10 amps. The current measurement range is actually quite impressive on this 6.5 digit meter. And you can see that in this lowest DC current measurement range of 2 microamps, the resolution is all the way down to 1 picoamp. Let's do a measurement of our current standard here. This is a 1 microamp current standard. Let's see how accurate our current standard is. And you can see the reading we're getting is pretty much spot on at 100 microamps. And in AC current measurement mode, you can see the lowest range is only 200 microamps, and of course the resolution we can get is only 1 nanoamp. Here I'm measuring the current using the 10 amp range, and right now the current is 100 milliamps. Because we have 6.5 digits here, even the 10 amp range has a resolution of 1 microamp. And you can take advantage of this dynamic range, and you can get very little burden voltage when measuring low current in this range. Right now you can see the burden voltage is only at 23 millivolts. Now let's take a look at the resistance measurement mode. First, we'll take a look at the 2-wire measurement. Now, the update rate of the resistance measurement also depends on the integration time. Obviously, the shorter the interrogation time, the faster the measurement speed. Let's actually short out the leads and get a sense of the speed of the auto-ranging. Well, it is not the fastest. It took about 2 seconds for the auto-ranging, but that's not what this meter is for. For a 6.5 digit multimeter, measurement accuracy and stability is the most important. Now you can see also we are overcompensating the probes a little bit. Right now we're measuring minus 0.1 ohm. Of course, we can always press the rel button to zero it out. Now let's measure a 10 ohm resistor and get a sense of the measurement speed. And you can see it took about 2 seconds, but if I change the power line cycle, let's just say to 0.006, and let's see how fast we're measuring it. And the update rate is pretty fast. Now, the actual speed is because of the auto-ranging here. So if I, for example, change it to the, let's say, 200 ohm range, and manually change the range, and you can see the measurement speed is really fast. So let's change it back. One feature this meter has is the hold measurement capability. Basically, when the meter detects a stable reading, it will hold that value. This is very useful when you are doing binning of the components. So let me demonstrate that here with the ohm measurement. To enable hold measurement, I'm just pressing Shift and single. And now I can do the hold measurement. So let's give it a go. And it took a few seconds. You can see that we are getting a stable reading of 10.13 ohm. As a bench meter, of course, it also supports 4-wire ohm measurements. So let's give that a go. Now I have hooked up these Kelvin clips, and by the way, these clips are not supplied with the meter. So let me change it to 4-wire measurement here. And while still in this probe hold mode, let's measure a couple of these 100 ohm precision resistors. You can see the first 100 ohm resistor we measured at 99.96, which is well within the specified 0.1% tolerance for the resistor. And let's measure another one of these 100 ohm 0.1% tolerance precision resistor. For that, I had to turn off the probe hold so that we can see the actual measurement speed. You can see this one measures 100.05, which is slightly higher than the last one we measured, but it's still within the 0.1% tolerance. Of course, we can also measure capacitance, and I have changed the probes to these alligator clips so we can clip onto the capacitors. In capacitance mode, you only have 4.5 digits. In theory, you can still measure small capacitance well into the picofarads range, as it does have a resolution of 0.1 picofarads, as you can see here. The problem is, as you observed, the display is jumping quite a bit. There's quite a bit of a residual capacitance. And that combined with a slow display update rate in this range, it might not be best suited for measuring small capacitance. Let's start with a 22 microfarads capacitor. And you can see the measurement speed is actually pretty slow, but we did eventually get that 22 microfarads reading. So let's try another capacitor. This time I'm going to try a 820 microfarads capacitor. And let's see the measurement speed, if there's any noticeable difference. Wow. That is pretty slow. So it's about a good 10 seconds now, and we're still not getting the results. So that took about, I don't know, 20 seconds, and we eventually get this 860 microfarads reading, but it did take quite some time. Now let's try an even larger one. This one is a 15,000 microfarads one. So let's hook it up. Wow, I'm not sure what's going on here. Is it able to measure this 15,000 microfarads capacitor? It should be able to, as the maximum value it can measure is 100 millifarads. So this is well within the range. I guess it's just slow, so let's wait. I don't want to cut the video here because I want to see exactly how long it takes to complete this measurement. As you can see, it's still going on here. Wow, that was painful. So I guess this 6.5 digit meter is probably not best suited for measuring capacitors. I have no doubt the measurement accuracy is high, but you will need to have a lot of patience. Just like the 8805E, this meter also supports temperature measurement. And let's give it a try. So let's first change the unit to Fahrenheit. And you can see we have the probe setting here. So this meter supports quite a few different types of probes. You can see here. Now this is RTD. Let's actually start with a thermistor because we still have the probes in here. So let's do a thermistor 2-wire. And let me just hold it down here. Now this is not a standard thermistor, so the temperature reading will be a little bit off. But we can take a look at how it works. And you can see we are able to measure the temperature. Of course, it's about, I think it's about 20 degrees off the measurement here. So let me put my hands on it. You can see, indeed, we're able to read the temperature. So that's the temperature measurement with the thermistor. Now let me unplug these. Now let's try the temperature measurement again with the supplied thermocouple. So you can see we have quite a few types to select from. Let's do K-type. Let me plug in the thermocouple here. And you can see we're reading 76 degrees. Let me put my hand on it. Yep, no problem. Now let's take a look at the continuity test. In this mode, you can actually set the threshold. Now let's just leave it as 30 ohm, which is the default here. And you can see it's pretty fast, and it does sound like it is latched. And let's take a look at the diode measurement. According to the manual, the maximum voltage output is 4 volts, so it should have no problem measuring a white LED. So let's give it a go. Yep, you can see we have no problem. And let's try a Schottky diode. And you do hear the sound. According to the manual, under 1 volt, you will hear this beeping. So that's not a problem. The UT8806E also has this dedicated frequency period measurement, and you can swap between these two using this button here. So now I'm showing the period, and I can show the frequency here. We have already seen the frequency measurement in action when using the dual display functionality while measuring the AC voltage. What I wanted to point out here is that if you change the gate time here, you can actually change the measurement resolution here. So right now we change it to 1 second. You can see we gained additional resolution on the frequency display here. Of course, if we change the gate time to be shorter, then the update rate is a lot faster, but the resolution would drop. So let's change it to the standard 100 milliseconds. The UNI-T UT8806E is packed with features. There's still quite a few things I haven't touched upon. For example, the acquisition button. You can change the delay, the trigger mode, and also you can control whether or not the VMC output is on or off. And of course, the mathematic function, you can use that to see the statistics on and off. So there's just so much you can do with this meter. But I think you've got an idea of what this 6.5 digit bench multimeter is capable of by now. In the next video, we'll do a teardown, so stay tuned. I hope you enjoyed the video. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.